Thanks for the introduction, Jim. Thanks too for the opportunity to showcase wireless charging. We're excited about the benefits wireless charging brings to the electric vehicle industry, and I'll start by giving a short background to our company to add some context to the wireless charging story. I'll talk about wireless electric vehicles and their charging, the benefits of IPT, the history of IPT or inductive power transfer, the technology advances that we're making, and the future directions of the technology. And I'll also touch in closing on some case studies which discuss a little more in detail about the deployment of the technology. Halo IPT was founded by Arup and Auckland Uni Services Limited. Arup is a global consulting engineering company who has huge expertise in deployment, design and deployment of transport infrastructure and large focusing really on the built environment, but they have a very deep knowledge in future transport and in future city design. Uni Services is the commercial company of Auckland University, and they over the last 15 years have been patenting new technology developments and commercialising those technologies in the field of wireless power transfer or inductive power transfer, IPT as we call it. The company was founded last year, and we've just had our first year anniversary, and we have funding from the Trans-Tasman Commercialisation Fund, which is a fund out of New Zealand and Australia. We're headquartered in the UK, and we're very much market focused rather than technology focused, even though we're a technology company, but we like to be led by the market rather than pushed by the technology. The objective of Halo IPT is to bring to market wireless charging for electric vehicles on a global scale over the next 5 years. You'll all know the curves which are showing the uptake of electric vehicles or electric vehicle sales, and that's both plug-in hybrids and pure battery electric vehicles. And I think suffice to say the main message is that the electric vehicle market is rapidly growing, and it's a huge opportunity for component manufacturers as well as car manufacturers. The domestic and overnight charging is likely to dominate, and so we're focused on providing technology into that stationary or domestic situation. And forgetting to plug in and lack of range are two big issues with vehicle charging, and they're front of mind for potential purchasers of electric vehicles. Wireless charging provides a solution to many of those problems. There are a number of issues with plug-in charging, from durability issues, aesthetics, convenience, safety and cost, that wireless charging provides solutions to. Wireless transfer of power is safe, it's impossible to enliven a vehicle, it's double isolated, it removes the electrocution danger, and there's nothing to corrode, no contacts, no plug connectors to corrode or short circuit, and there's no trip hazard because the technology is beneath the pavement. There's no plugging or unplugging to be done, no stained clothes or dirty hands from cords, no moving parts to fail, it's waterproof and weatherproof, no need to brave the weather yourself to plug the vehicle in, and the charging is automatic, so there's no way of forgetting to charge. One merely parks and the charging starts. The charging infrastructure is low profile and very difficult to damage or vandalise. There's no cord to steal or unplug, and it's impervious to chemicals and works beneath snow and ice and water. Very, very low risk, and that translates into a low insurance risk. It doesn't damage the precious aesthetics of historic cities, avoids unnecessary street clutter, maintains our precious footpath area, and removes the eyesore of overhead cables in situations of bus charging and trolley bus charging. It's easier to charge, therefore the car will be in a charging situation more often, and the batteries ultimately could be smaller and lighter and make the vehicle a cheaper proposition. It's important to note that IPT or inductive power transfer is not a new technology. It's a technology that's been around a long time and is proven in industry. It has a legacy in materials handling, factory automation, car assembly, those sorts of applications, and it's been well proven. Auckland University's been at the forefront of developing technology that's been commercialised by a number of licensees, both in car assembly and materials handling, and in clean room factory automation, in the semiconductor industry and the LCD industry. And the technology is very robust. It creates no residues. In the clean room environment, it's a perfect way of transferring power. And in the materials handling and car assembly applications, it's very safe. There's no way of tools being dropped across a contactor, etc. So it's been very, very robust and well proven in industry. There are challenges in moving from the industrial application though into an auto setting, and they are that the industrial applications tend to have a very, very low gap that the power transfer is occurring over. The vehicles, AGVs, automatic guided vehicles, cranes, etc., follow a very, very tightly guided route, so the lateral tolerance of the system is quite low in requirement, and also the emissions standards within a workplace are different because it's a notifiable environment. So in moving from the industrial setting to an auto setting, we had to overcome a number of challenges, and that was really to get the technology suitable for use in the public environment, so getting on top of emissions, meeting other stringent regulations, ensuring we could put power across a bigger gap, so instead of inches we're talking about tens of inches, and making sure that the technology had suitable lateral tolerance or insensitivity to misalignment, so that it was available as a pragmatic solution for people parking their vehicle. Obviously it's not much help if people have to be sort of millimetre perfect when they're parking a vehicle before power will transfer effectively. Also, what's critical in the deployment of IPT in a public setting or in a mass market setting are safety and efficiency. So from a safety perspective, we ensure that the technology is inactive until a car is parked over the ground infrastructure, so the pad will not turn on until an IPT vehicle is above and has communicated effectively that condition. We have safety sensing and shut-off for foreign objects between the pads, and we make sure we focus very squarely on the IC and IRP regulations and ensure that we meet the levels of magnetic field emissions that are required under those guidelines. We also are focused on ensuring that there's no electromagnetic interference into sensitive vehicle electronics, and we do that by shielding the hardware on the vehicle also. From an efficiency perspective, the transmission from the plug in the wall to the battery is comparable to a cabled system, and that means that we're getting a grid to battery efficiency of over 90% in most instances, and a pad to pad efficiency of over 97%. So very low loss in the total system, and in fact it's comparable to many of the plug-in chargers that are on the market. And the efficiency is only slightly affected by misalignment. So when we park a vehicle and it's, for example, 4 to 6 inches off centre, then we'll still be delivering power at a couple of percent off the target efficiency of sort of 90-92%. And that's important because we don't want a system which provides power over a broad range of proximity but has poor efficiency when it's misaligned and good efficiency when it's aligned. So that's one of our key focus points too. Halo IPT technology provides a unique combination of benefits. The devices we produce work at power levels of 3, 7 and above 18 kilowatts. We have high transmission efficiencies. We have high lateral tolerance to misalignment, as I mentioned. And we can put power across gaps of up to sort of 300 millimetres or 12 inches whilst having a lateral misalignment of 4 to 6 inches quite comfortably. We're also tolerant to a wide range of change in vertical gap, which is important for when a vehicle is laden versus unladen. And we have unique magnetics in our pads, which ultimately means that they are a smaller form factor, lighter and cheaper to produce than many of our competitors. Systems based on the original technology developed at Auckland University have been operating in the commercial arena for many, many years. And in fact, we have technology operating in two cities in Italy, in Genoa and Turin, with high-powered IPT systems working on buses there. This experience provides a sound base for addressing the questions of in-field performance, reliability, and public health and public perception. I think at this point it's worth giving a high-level overview of the technology and what the component parts are. The IPT has 4 or 5 different elements to it. The first is a power supply, which is a high-frequency generator effectively, which takes power from the grid at 50 or 60 hertz, turns it into 20 kilohertz or above, and that is cabled up to a ground pad, which is embedded in the road or in a car park or in somebody's garage. And when turned on, the high-frequency generator will produce a very, very strong magnetic field above the pad on the ground. There is then a complementary pad on the vehicle that picks up the magnetic field that's being produced on the ground pad, and then that is cabled up to a controller on the vehicle, which is then converts that high frequency AC signal back into DC and sends it off to the battery of the vehicle. Now that controller also communicates with the battery management system, has CAN bus interfaces so it can communicate with the vehicle, and allows us to communicate to the user, so we have the user interface in there as well. So the whole system effectively is a power supply, a ground pad, a pad on the vehicle and a controller on the vehicle, and then some logic and software, control software, which is running the system. In addition to the base system, we have a number of technologies in development also, such as vehicle to grid, and this is important for delivering, or the ability to deliver power from the vehicle back into the grid to allow distributed storage, for example, load levelling, etc. And really is a key part of the future smart grid enabling of electric vehicles. We're also developing dynamic charging, or charge on the move as we call it, and this is where a vehicle could pick up power while it's travelling along a suitably designed road with charging infrastructure embedded in the road. This is really key to solving the problem of range anxiety. Another exciting technology under development is dynamic charging, or charge on the move. This is where we place transmission pads in a contiguous line or a charging lane, allowing batteries to be charged as the vehicle drives along. Dynamic charging will reduce the size of battery requirement quite substantially, and in fact in a case study I'll touch on later we can see some real numbers around that. Dynamic charging will reduce range anxiety, as having lanes linking cities or towns will mean that the vehicles are only required to go as far as certain interstate highways before charging is offered during the travel period itself. Another very important developmental area that we're focusing on is the area of interoperability. And this is to ensure that our wireless charging technology is interoperable with our competitors. This is important to ensure mass market uptake of electric vehicles. We've achieved quite a lot in the last 12 months, from development of bench test systems through to fitment onto vehicles of low power systems at 3 kilowatts, up to 3-phase 7 kilowatt systems, and development of bench test prototypes for higher powered beyond 18 kilowatts. The slide shows a timeline of those achievements. Our future program has 2 distinct phases, from the early development phase through to market entry phase. The development phase is focusing on R&D elements of reducing cost improving compactness and form factor of the technology on the vehicle side, increasing power capabilities for buses, large vans, etc. Continued interoperability work, vehicle to grid studies. Our market entry has two distinct phases, the first being an earlier phase where we're focusing on the emerging vehicles, or the niche providers of electric vehicles, and they are in the levels of hundreds of systems, moving through to the buses and fleet users, which are numbering thousands of units, into dealer fitted options, which would move into higher volumes of tens of thousands of units. The second part to our market entry is to secure long-term income streams. That is to develop manufacturing capability for the primary side and to develop partnerships with the automotive supply chain for the secondary side, or the on-vehicle side. I would like to now provide three case studies showing how the technology is used in real situations around the world. The first is a bus system in Turin with 20 vehicles. It's been operating since the early 2000s with a very high degree of reliability, no problems with weather, it gets very hot and very cold in Turin, and no public health or safety issues. The route is a 15-kilometre route and the bus operates all day, starts the day fully charged and tops up at the end of each route on each duty cycle. And what that's meant is that the battery on the bus has been reduced from a predicted 135 kilowatt hours down to 45 kilowatt hours. So it's about a third of the original size. So that's provided an exceptional cost saving from the battery perspective and the total bus system perspective. The second study focuses on a small vehicle trial. The vehicles have 3 kilowatt charging units fitted to them, and they are monitored under the UK's cabled project. That is looking at performance attributes and usability. In a broader sense, the trial has 100 electric vehicles in it and a small number of them with IPT systems fitted on. And this provides great data comparing the plug-in system with the wireless charging system. The third case study revolves around a high-powered three-phase system, a 7 kilowatt system fitted to a Rolls-Royce Phantom experimental electric vehicle. This was a system that was fully integrated into the vehicle's electronics and driver interface and publicised prior to a launch at Geneva Motor Show, and the vehicle is now on a worldwide tour of its potential markets. In summary, while challenges exist in plug-in charging of electric vehicles, wireless charging using IPT provides a number of solutions. The technology is proven in industry, it's been migrated effectively to the auto industry, and efficiency and safety issues have been overcome. There is also an exciting development potential for wireless power. Thank you for listening, and back to you, Jim.
How quickly does a car charge?
Charging a vehicle using wireless IPT charging takes about the same time as with a conventional plug-in system. So for a vehicle with a 15 to 20 kilowatt hour battery, it would take around about 5 hours to charge from zero to full.
Does the system make the car any heavier or lighter than a normal car?
Well, initially there is an additional weight to the vehicle in the onboard infrastructure or onboard hardware that we put on the vehicle. With time, when we reduce the batteries through a ubiquity of charging opportunities, then the car would become lighter and cheaper to manufacture.
What types of company are most interested in this technology?
Well, we've had a huge interest from the traditional Tier 1 and OEM, auto OEMs, who see the benefit of wireless charging and are very excited about this new technology for solving a number of problems with the plug-in systems. Now, wireless charging is inherently safe. The system is double isolated, so it avoids any risk of electrocution that comes with a plug-in system. It also the magnetic field emissions are also in a similar range to an inductive cooktop. So through magnetics design and understanding the shielding, we can make the system inherently safe.
Will this affect my mobile phone and my other electronic personal items?
So the magnetic field is shielded in the pads on the vehicle and on the ground to ensure that there's no field or no emissions into the vehicle. And the system only turns on when there's a car above it. So your credit cards, mobile phone, etc. are all protected or shielded from any magnetic field.
What can government and industry do to encourage the infrastructure rollout?
I think we understand that the initial charging will happen at home, and so the initial infrastructure will be put into people's garages. We've worked on a basis of 2 chargers for every vehicle, the first one being a domestic charger, the second one being either in a public place or a workplace. What governments can do to push this through is to convert their own fleets to electric vehicles and really support the electric vehicle industry by leading by example.
What is the potential for the electric car market with wireless charging, dynamic charging and smart grids?
Well, I think we move into a situation where a wireless electric vehicle will have no range limitation. It can have a very small battery, so it can be a light, cheap form of transport, high performance. And really the electric vehicle with a wireless charger with a dynamic infrastructure in place provides the ultimate in new clean green technology with no range limitations that's affordable.
How will this make EVs more attractive to people who live outside of cities and major towns? Or is it be too difficult to provide rural coverage?
No, I think the contrary is true really. I think the people who can drive their vehicle into the city and with the ubiquity of charging opportunities, pick up, charge a little and often charge opportunistically as they go about their daily drive, means that they'll have more confidence to use their electric vehicle and will provide more a broader range of use, so the vehicle isn't bound to just an ultra-urban setting.
How do I find out more?
My contact details are at the end of the presentation. Please feel free to get in touch or visit our website at www.haloipt.com. Okay. Thank you for listening. Back to you, Jim.